So let's look at integrals of value functions, of vector functions. So recall, we're going to go over a tiny bit of integration again, just to make sure you do not forget it briefly. These can come up in this course, like old integration methods do come up at times, so they get discussed again real quickly. Make sure to. But these are these are very important to know, especially this form, the general form of, you do it 1 raised to a power, some kind of variable raised to the power, any type of power, except for 1. Think that, no, that should be -1, or whatever. It cannot be -1. Because x to the -1 power would be is a special type of integral for that equals the natural log of x. In this case, it was x to the -1. So, point is that n cannot be -1, basically. But otherwise, it's xn plus 1 divided by n plus 1 plus a constant when it's just like this. When you have definite integrals, it does not have a constant. And of course, it's just one form of writing the basic form of a definite integral, but you'll see in the examples. This first thing, you basically integrate part by part, similar to how you take derivatives for each component. And the integral of t cubed, integral, with 1 and 0 as definite parts, was 7, and for t plus 1. So it's t cubed is t to the fourth power divided by 4, because this is 3, as I show down here, you want to see all these integrals in depth, indefinite form of it, which is not used for definite. This, all the evidence is that c is not in it. Is that t cubed is t of 3 plus 1 power divided by 3 plus 1, n plus 1. But yeah, you can read this on your own. I'm not going to take forever to explain basic integration, especially this type. But you can see it. Try to make it show a little bit. In the end, you plug in 1 and 0 and subtract when t is equal to 1 and t equals 0. The expression inside. And of course, I, j, and k are kept from the beginning in the same area. And then you get 1/4 I plus 7j plus 3/2 k. But generally, it's just integration, definite integration here. 1 to the 4th power divided by 4 minus 0 to the 4th power divided by 4 would just be 1 to the 4th. 1 to the 4th is 1, so it's 1 divided by 4. 7 times 1 minus 7 times 0 is just 7, because 7 times 0 is 0. So 0 is 7. And of course, t plus 1 becomes, integrated, it's t squared over 2 plus 1t. Technically, you can separate it, do it by, like, this works out. Yeah, the subtraction, because it's 1 and 0, is just minus. It's basically minus 0, so of course. Comes 1 over 2 plus 1, which is 3 over 2. There's only a couple palms here. Of course, some tricks sometimes they can be slightly tricky. Here you have to know your trig integration, which I kind of detailed on here, like it's opposite of the derivatives of the trig functions. So when you have sine ti plus 1 plus cosine t j plus secant squared t k. You take integral of pi fourths, negative pi fourths. One thing to note is that, secant squared, and what it becomes is tangent t that's defined within pi fourths to negative pi fourths. It's fine because it's defined in that range. If it was not defined for part of it, then it would be a problem. Like, you can't, tangent of pi halves, let's see, that's sine over cosine, so cosine would be equal to 0 in that case, and you can't do division by 0. Therefore, tangent is undefined at pi halves. So if that was included, that would be a problem. But it's not, because it would not be continuous. And derivatives and integrals are taken with the knowledge that the function is continuous. Just something to note. I don't think that's ever really used much in undergraduate math, too much, those types of tricks enough. But it's always something that can be an issue. I feel like could be a trick, but not many people want to do it. You gotta just worry about the computations at times. But so you have this. So the integral of sine of t is negative cosine t. 1 plus cosine t, while integral of 1 is t, and integral of cosine t is sine t. Okay. And that's because derivative of sine t is cosine t, derivative of negative cosine t would be sine t. These go to reverse, and then of course derivative of tangent t is secant squared t, so secant squared t's integral will be tangent t. With trig functions, it's literally just reverse. It ain't like a fancy, And of course, he's all done with the brackets for pi force and negative pi force. That's one way of writing it. For what the t values, those are the t values up there in the brackets. And I wrote it out, trying to write it all out here. But yeah, it simplifies down pretty quickly, no matter what this looks like mess. Pi force is a definite number of square root of 2 over 2. Your cosine of that as well as sine of that same thing. And tangent of pi force is 1. Negative pi force tangent is negative 1. When you have sine, you have to just you should know this pretty much. But it's written out if you need it, and eventually you get just. I becomes 0, so it gets cancelled out. You get 2k, and you have pi plus 2 square root of 2 over 2, j. Now it's time for the funner part, the better part. The initial value problem for r as a vector function of t. So you have the differential equation, and you have the initial condition. Even this for two problem types. This one, and there's courses on differential equations that focus a lot more on initial value problems, at least to some extent. And integration is very important for these. But regardless, r of t is equal to the integral given negative ti minus tj minus tk. Yeah, it's just negative, it's like very basic. It'd be the same exact same for both I, j, and k basically. And negative t to the, negative t squared divided by 2 and negative t squared, for all the components. And you add c, it's an indefinite integral, you see. So you add the constant c, and eventually, then you plug in r of 0 to get, basically 0i plus 0j, minus 0j minus 0k, because 0 squared over 2 no matter is going to be 0. And it's plus c is equal to, of course, from the initial condition, I plus 2j plus 3k, and then c is equal to I plus 2j plus 3k. Which is a somewhat common trait of these types of initial value problems, is that a lot of things cancel out right away, at least in this section. And then RT you can write as equal to what's originally plus I plus 2j plus 3k from the c value, basically just plug in c, and that's your answer. Well, you simplify by adding components together, like you can add different vector components. Comes, what's here? 1 minus t squared over 2, and then you have 2, because you're adding, and adding to negative, you just subtract. And 3 minus t squared over 2, It's mostly written here. There's not much, I don't think there's anything too hard to explain besides some specific integrations, or this section especially is pretty simple. One more problem before I even think about anything else to discuss. You're given a second derivative, and you're supposed to get back to the initials. You have two initial conditions for the first derivative as well as the initial position function. So it's a little bit more interesting here. You have to start all the way from the second derivative and get your way back to the initial position function. It's a relatively simple one. Negative 32k is pretty simple, second derivative still. So you integrate. Technically, it's d dt of dr dt. Just saying that. Then you integrate dr dt is equal to the integral of negative 32k, which equals negative 32 basically it's negative 32t. I put t to 0 plus 1 divided by 0 plus 1, so it's going to be just divided by 1 in the end. Negative 32t divided by 1, which is negative 32t. It'd be just to try to show you off that basic, one of the more important integration techniques is using that general power formula. Really common. Negative 32tk plus c1, and I put c1, c2 in the end because there's two different constants because we're going to have to integrate twice. But yeah, it's the first derivative, is equal to this because you integrated from the second derivative to get the first derivative. Equation for it. Negative 32tk plus c1. And then the initial condition is when t equals 0, that 8i plus ha is what the derivative is equal to. And that's equal to negative 32 times 0k plus c1. This can't, so 0k plus c1 equals 8i plus ha, which means that c1 is just equal to that, to the initial condition. So you plug it in and you get negative 32tk plus 8i plus ha, and I can rearrange that to 8i plus ha minus 32tk. Good. And then you have to integrate this expression, integral of dr equals integral of 8i plus ha minus 82tk dt, and you integrate each component to get RT. It is 8ti, it gives you basically an 8tj, and this one is negative 32 constant, so it would be pulled out when you integrate technically t squared over 2, so it's negative 32 t squared divided by 2k plus another constant c2, a different constant, and then of course simplified down it's negative 16 t squared k and everything else the same. But you can do, because negative 32 divided by 2 is negative 16. And from there we go to the last part where we do the initial value of R0. It's all equal to 100k. The R of 0 is 100k. And 8 times 0 is 0, 8 times 0 is 0. Negative 16 times 0 squared is 0. And that's all, and that's basically the 0. So C3 is equal to 100k. It's fairly simply put. So in the end, you add the components together for your final thing to get 100 minus 16t squared k. You basically it's 8ti plus 8tj plus 100 minus 16t squared k. It sounds weird saying it out loud. That's why I try to. But that's the answer. Some extra notes. Of course, these integrals cosine t dt equals sine t plus c. They're indefinite. Integral of sine t dt equal to negative cosine t plus c. The integral of secant squared t dt equals tangent t plus c. And integral of t to the n dt equals tn plus 1 divided by n plus 1 plus c. Ignore that. N does not equal 0. No, that's wrong. Point. I always don't know what I'm right, but it should be n does not equal negative 1. As I said, t to the negative 1 dt would be, the integral of that would just be the natural log of t. Because the natural log of a variable, like t let's say, is equal to, derivative of natural log of it is 1 divided by t, let's say, which is t to the negative 1 power. So that's why it's n is not equal to a certain value, negative 1, for that general power rule for integrals. But as you can see, basic integration for these sections, but in another section or two you basically see more integration stuff come up. So it's good to be able to understand the basics of integration in this course. Not really to Calc 2 integration, but more to Calc 1 integration stuff is more needed.